Hi there, how's it going? Terry Brown, Mechanical Engineering here to solve another engineering mechanics problem. So let's get into the problem. Okay, so in this problem we've got a loaded structure with three forces acting on the top here. So this is some kind of bolted and welded structure designed to carry these loads, and in the question we're asked to replace the force system acting on the frame by a resultant force and couple moment at point A, so down the bottom here. The reason for doing something like this in practice is if we need to design the support here, so if we need to know, what size gussets here to make, if this is going to be bolted down into the concrete, how many bolts we need, what size and grade they need to be, the concrete, we need to know what strength that needs to be, and the step that we need to go through in order to do that is to find the resultant force and moment acting here. So in fact, we don't even really need the resultant force for those calculations. What we would actually want would be the normal force, the force normal to this connection, and also the shear force. So they're the things that we generally need when doing a bolted or welded connection like this. All right, so let's go through the problem as written. So just to work out what the resultant force and moment are at point A. In this problem, we don't need to go any further than that. But in the textbooks, what they also often will ask you to do is to find the location where the single equivalent force acts. Okay, so this is a useful thing to know, but not quite as important as being able to work out the resultant or the resultant component forces at various locations and the resultant couple moment. So we might also need to do it here at this connection at B, for example. So you could do that as an exercise for yourself. All right, so our solution. So firstly, to find our resultant force, we're just going to add up all of the forces or all the components of the force in the x direction. So we've got 1, 2, 3 forces, but only 2 of them have components in the x direction. So if we start by looking at each of these forces, so starting with the force on the left here, the 5 kilonewton force. So you can see here I've just made use of the 3-4-5 ratio triangle here. So my horizontal component down here will be just 4/5 times 5. And that will be in the positive direction as I've defined it here. And then if we go over to the other side, we've got this 3 kilonewton force. And again, rather than being given angles, we've got these ratios. In this case, it's 5, 12, 13. Okay. So if you do your Pythagoras theorem, square root of 5 squared plus 12 squared equals 13. So yeah, so in the horizontal direction here, we'll have 5 over 13 times 3 gives us our horizontal component. So if we do our sums, we'll get 2.846 kilonewtons in the positive direction there. All right, so now let's look at the y direction. So let's look at each of our components, our forces in the y direction. So we can see that all 3 are going to be acting in the downwards direction, so they're all going to be negative. So let's start with the one on the right. No, the one on the left here, so 5 kilonewtons. So using our ratio of our triangle here, 3/5 times 5 will give us this vertical component. Minus 2, vertical component is just the force itself, no horizontal component for that one. And then we have the vertical component of this force here, 12/13 times 3. Do our sums and we get minus 7.769 kilonewtons. All right, so now we need, now we need the moments, but first of all, I'm going to find the resultant force here. So we've got the resultant components in the x, resultant components in the y. To get our absolute resultant, again, use Pythagoras theorem, square root of sum of the squares. So rx squared, square root of rx squared plus ry squared. And we do that and we get 8.274 kilonewtons. And if you want to know the angle, so it doesn't matter which angle you find, I've found this one in here. So the opposite will be ry and the adjacent will be rx. So from theta equals inverse tan or a tan, opposite over adjacent, so ry over rx, put in the values and we'll get 69.9 degrees. Now let's look at the moments. So if we want to know the resultant moment about this point down here, point A, we need to work out the moment effects of each of these forces, or the components of each of the forces. Will probably be easier. So rather than working out the perpendicular distance from the line of action of this force here, for example, perpendicular distance to point A, it's because we've already been given these horizontal and vertical dimensions, it's going to be easier to find the vertical and horizontal components and use their perpendicular distances. So using the principle of moments and Varanon's theorem that we looked at previously, that'll be the easiest approach. All right, so let's work our way through that. So sum of the forces times their distances to point A, taking anti-clockwise as positive. So first of all, our first component here will be 4/5. So we've got the horizontal component of this force. So let me just draw that in for you. Okay, so that's that horizontal component. So 4/5 times 5, and its perpendicular distance is this distance here that we have 5. Right, so continuous line of action, perpendicular distance to point A is 5 meters. So that's what we've got here. And it's tending to rotate this thing around in that direction, which is clockwise about point A. So therefore we have negative at the front here. All right, so let's get rid of that one. Then next we have the vertical component. So let me draw that one in again for you. Alrighty, so there's our vertical component. So 3/5 times 5, which is what we've got here, times its perpendicular distance to point A. So it's continuing its line of action down here. Perpendicular distance to A will be this dimension here that we have 4. All right, now let's consider whether it causes a clockwise or anti-clockwise rotation. And I think hopefully by now you can see that about point A, that's going to cause a rotation around that way. As I've said to you before, just grab a pen or ruler, put your finger where you're taking moments about and push down and see which way it goes. Okay. Work out whether it's clockwise or anti-clockwise. With the one that we did before, we had point A and we had a force going horizontally. Just push and see which way the force is generating the moment. Okay, so next we have the 2 kilonewton force, just a vertical force here, so no horizontal component. Its perpendicular distance to point A is 1 meter that we've got here, and we can hopefully see that that will tend to rotate that way around point A. So that one's a clockwise moment. So therefore we have a negative sign out the front. Let's get rid of that guy. Then move on to the 3 kilonewton force out on the end here. Okay, so our horizontal component here is 5/13 times 3, same as we had up here. And its perpendicular distance is 5 meters, the same as we had the one over here. So let me just draw that one in again for you. Okay, so here it is up here, pushing across to the left. So hopefully we can see that that is going to cause a rotation that way, which is anti-clockwise, and its perpendicular distance is this distance here, 5. So that's what we have here. So the force component in the horizontal direction times its perpendicular distance, and it's positive because it's going in the anti-clockwise direction, and that's what we've defined as positive. And the next one is the vertical component. Draw that guy in. Right, so there's the vertical component. Its perpendicular distance to point A will be 2. Right, so it continues down here. Perpendicular distance to point A is 2. And you can see that that's going to tend to rotate clockwise about point A. So therefore we have minus sign out the front. Okay, so that's it. So we can put all that into our calculator and calculate that we get a resultant moment of minus 9.769 kilonewton meters. Okay, so the minus sign indicates that our resultant moment is clockwise, because we assumed anti-clockwise is positive. Right, so just summarising our result, the resultant force is 8.27 kilonewtons at an angle of 69.9 degrees down from horizontal, and our resultant moment is, or resultant couple or moment is 9.77 kilonewton meters clockwise. All right, so that's the first part of the question. The next part was to find out what the location of the equivalent single force, right, whether it acts above or below. All right, so let's go through that. So just redrawing the bottom part of the structural frame there, putting on my resultant force and moment that we've calculated. All right, so to find the location of the single equivalent force, we need to move that force somewhere such that it provides the same moment that we calculated here. So if we put it somewhere, now I think we can see hopefully that in order to get a clockwise moment, we're going to have to move this up somewhere, or this is going to need to be placed somewhere above point A for it to generate a clockwise moment about point A. All we need to do now is to work out how far. Right, so if we just label that unknown distance as D, and if we notice that our horizontal component acts there and our vertical component of our force, its line of action passes through point A. So therefore, the component Ry is not going to have a moment about point A. So all we need to worry about is Rx. So if we do Rx times D and make that equal to the moment that we calculated up here, then that will tell us where we need to place this resultant moment so that we have an equivalent single force that's the same as our force and moment that we had before. Okay, so I've just put in here, as I've said, that Ry passes through point A, so therefore its moment about point A is 0. So now we can just do a simple calculation, put in our values that we calculated before, 9.769 for the moment, and the horizontal force was 2.846 kilonewtons, so we get 3.43 meters. All right, so just to summarize all that, we started off with 3 individual forces, and we found the equivalent single force and moment that acts at point A. Okay, so this, what we have here, is equivalent to our 3 original forces in terms of the external effects on the body, right, on this structural frame. And as a practical application, we would use these, and in fact would use the vertical and horizontal components that I've shown here in order to design this structural connection. Right, so we would need the shear force, the normal force, and the moment at this structural connection in order to design the details for this. And then as a next step, sometimes we want to know the single equivalent force. Not so often do we need this in static problems, in structural analysis, but often we want to do this in dynamic analysis to find the single equivalent force. So we did that as well, just as a bit of an extra calculation. So what we see here at the bottom are 3 equivalent systems. Okay, so these 3 forces here are equivalent to this single force and moment that we calculated, which is also equivalent to this single force applied 3.43 meters above point A. All right, so that's the end of the problem. So I hope you found that helpful and interesting, maybe. Yeah, so that's it for now. I'll see you in the next video. Or I won't see you, but you'll see me. Bye for now.